Welcome. In the last class, we have seen what is the origin of drag force, origin of lift force, and how do we make it dimensionless in the form of drag coefficient and lift coefficient. Same way as drag coefficient, we can define lift coefficient. Although we didn't see the definition, but you can just extrapolate. It will be lift force divided by the projected area and half rho v naught square. So this is where we are with respect to our course. We are on flow past immersed objects, external flows. Just before we start, just to revise, make you revise concepts that we have learned in the previous class. First of all, what is meant by adverse pressure gradient? Why does boundary layer separation occur? What is the relationship between boundary layer separation and drag force? What is meant by drag force and lift force? And how are drag and lift coefficients defined? So answer these questions for yourself, and that will be a sort of revision of what you have done in the previous lecture. What we are going to see now is, in chemical engineering, we very commonly come across situations where flow happens across or around a spherical particle. So one example of that would be, let's say there is a gas bubble and we want to absorb part of that gas bubble, or let's say the gas bubble contains carbon dioxide or H2S, and we want to absorb that in, let's say, a liquid which is containing an acid, which is containing basic solution, let's say NaOH. So the flow, we make this bubble go through a pool of liquid, right? So that's a situation as if the flow of the liquid is around the bubble. Okay, so this is a situation of flow past a bubble. Same way, we might want to be separating solids from liquid. So the solid particles settle in liquid. Okay? Or we have seen dryer. Sometimes the dryer is operated such that the gas and the solid particle to be dried are taken together. They travel together, and as they travel in a pipeline or in a reactor or in equipment called as a dryer, the particle gets dried. So in numerous situations, we come across a situation of fluid flowing around a particle, or even simple situation like filtration, where we see that there is a bunch of particles and the flow of liquid goes around that particle. We remember we talked about filtration in MEBC. We talked about a filter cake. Cake is consisting of solid particles, and the liquid goes in between the gaps between those particles. Or we talked about, or say for example, water purification. How do you purify water in your houses? Suppose there is an aquaguard. That aquaguard contains a bed of carbon, and water flows down that bed of carbon, and thereby water gets purified, disinfected, and so on and so forth. Dirt gets removed, color gets removed, and so on. So this situation is, or water purification. We use ion exchange resins. As you go to your second year, third year, you will see what is an ion exchange resin and how does it work. But you have a bed of ion exchange resin, and the water flows around that bed, or inside that bed around the particles, and then the ions from the water get exchanged, and then that's how the water is purified. So there are numerous examples of situations where we talk about flow of fluids around a particle, single particle or a bed of particles. What we are going to start with is looking at flow of a fluid around this particle. Okay, so imagine right now there is a stagnant liquid, right? So the liquid is not moving, and this liquid, let's say, well, let's just draw that liquid if you want. Okay, so imagine that there is a liquid all around this particle, and this liquid, or in general it can be a fluid, it can be a gas, or it can be a liquid, and this fluid has a density different from the particle. Now we have seen in our macroscopic balances of force balances lecture, there will be a gravitational force acting on this particle. there will be a buoyancy force acting on this particle. And if the particle is more dense than the liquid, gravitational force will be more than the buoyancy force. This liquid particle will settle down. And if liquid particle is settling down, it is equivalent to saying that the fluid is flowing around the particle in the upward direction. So the direction of the fluid flow relative to particle would be like this. Direction of the fluid flow relative to particle will be upwards, because this solid particle is settling downwards because it is more heavier, more dense than the liquid. Gravitational force is more than the buoyancy force, and here these boundary layer separation will happen. Right? So there will be three forces acting on this particle. There will be a gravitational force, there will be a buoyancy force, and there is a drag force. I want you to write expressions for these forces. Okay, pause the video and write these expressions for yourself. Here are the expressions. Gravitational force Fg, let's say, is pi by 6 dp cube, volume of the particle, density of the particle, that will give you mass of the particle, multiplied by g, that will give you the gravitational force on the particle. Buoyancy force on the particle will be pi by 6 dp cube, volume that is displaced, multiplied by rho of liquid that is around, into g, that will be buoyancy force. The dp is the particle diameter. Particle diameter, this is dp. Let's just say this is dp, spherical particle. So this particle diameter is dp. Drag force, what will be the drag force? It will be CD, drag coefficient, multiplied by pi by 4 dp square, that is the projected area, multiplied by half rho v square. Now which v is this? This v is the velocity of the fluid relative to the particle. It is the relative velocity. Relative velocity of the particle relative to the fluid, or fluid relative to the particle. If fluid is stationary, this velocity, relative velocity, is the same as the velocity of the particle settling down. Now suppose I am holding this particle, right, and I allow this particle to go. I have released this particle slowly. What happens? Initially velocity is 0. If velocity is 0, what happens to drag force? Drag force is 0. Gravity force is larger than buoyancy force. This particle starts accelerating downwards. As the particle accelerates downwards, this velocity increases, drag force increases. So imagine that initially, let's do like this. Initially, let's say velocity is 0. So let's say velocity, gravitational force, buoyancy force, and let's say drag force. Okay, let's write these three forces. So initially, let's say velocity is 0. Gravitational force is, let's say, 10. Some value, just take 10. Buoyancy force is, let's say, 8. Right? This particle drag force is 0. So there will be a 2 Newton downward force. It will accelerate the particle. Accelerate the particle means velocity will increase. Suppose velocity increases to 1. What happens to gravitational force? 10. Does not change, does not depend on velocity. What happens to buoyancy force? 8, does not depend on velocity. Let's say drag force is 1 because the velocity is increased now. It's proportional to 1 square, so don't worry about it. We'll see the dependence as we go along, but let's say it is 1 right now. So the net force is 10 minus 8 minus 1. Now the net force is 1 Newton. So acceleration is reduced. It is still accelerating. Velocity goes up, let's say 2. So this becomes 10, 8, and let's say this also becomes 2. Because this CD itself will depend on the velocity. Let's not worry about that just now. So now the drag force is exactly balancing the gravity minus buoyancy force. Net force on the particle is 0. If net force on the particle is 0, that means there is no acceleration of the particle. That means particle moves downward with the same velocity, with velocity which is constant. We call this as the terminal velocity, Vt. Okay, that's what I have written here. Acceleration is equal to gravitational force minus buoyancy force minus drag force. As velocity increases, drag increases, and as the drag increases, the acceleration becomes lower and lower. Finally, acceleration becomes zero, means gravitational force minus buoyancy force exactly equals to drag force, and we call this as the terminal velocity. Okay. What we would like to do now is to calculate the magnitude of this terminal velocity for different kinds of particles. Okay, so this is what we are doing. How is the CD versus RE relationship looking like? This is the graph from the previous lecture. This is for a spherical particle. At low Reynolds number, how are we going to define Reynolds number? We are going to define Reynolds number for the particle. It is dp, particle diameter, multiplied by velocity, remember, we were talking about Reynolds number in a pipe. What was the value? D, diameter of the pipe, rho of the liquid that is flowing in the pipe, velocity of the fluid in the pipe, and mu, viscosity of the liquid in the pipe. Now what we have to define the Reynolds number for this particle as it is flowing. When this particle is flowing, what is it that is causing the boundary layer separation? It is the flow of liquid around. How is the flow of liquid around? The flow of liquid around is like this. That is what is causing the drag. So what is the cause of the drag? It is the cause of the drag is flow of the liquid relative to the particle. Flow of the liquid relative to the particle. That's why these are liquid properties. It is not the solid density, it is the density of liquid. Or in general, it could be a gas. The solid particle could be settling down in a gas, like a dust particle settling in air. Then this would be density and viscosity of the fluid. Is the liquid and density and viscosity of the fluid. That's how we define Reynolds number. Okay, you see three different regimes. One is regime below Reynolds number 1. That's called as Stokes regime. And you might have heard of Stokes law or Stokes drag. That is defined as Fd equal to 3 pi dp mu and the velocity. In this particular case, it is the terminal velocity that is reached. So this Reynolds number should have a terminal velocity. We should call it as a terminal velocity. And therefore drag force is also dependent on the terminal velocity. Now I can rearrange this. I can divide this by, so this drag force, if I divide, so 3 pi dp mu, it is mu of the liquid Pt divided by half rho v square and projected area. Projected area is pi by 4 dp square. And half rho velocity. Which velocity? Again, rho is of liquid. Which velocity? It is the relative to the particle, velocity of the fluid relative to the particle. In this particular case, we are talking about the terminal settling velocity. So this is CD, drag coefficient for the particle. And you will find that the drag coefficient is related to the Reynolds number as 24 by Rep. This expression, if you evaluate, if you simplify, you will get it as 24 by Rep. Check it for yourself. There is another regime here beyond Reynolds number of 1000, at which the drag force or the drag coefficient is approximately the same, approximately constant. That's called as drag coefficient of that value is 0.44. It is the value for a spherical particle, not for any other particle. Not for ellipsoid, not for aerofoil, nothing. It's only for spherical particles. CD is 0.44 in this regime. So that's a second regime beyond Reynolds number of 1000. In between, we have drag coefficient changing as a function of Reynolds number, not in a linear manner but a different manner. And one expression that is used very commonly to describe the Reynolds number versus drag coefficient behavior for all this area, for all the entire region, it is expressed by this expression. CD is 24 by Rep. That takes care of the first part, Reynolds number less than 1. CD is 0.44 0.4 in this particular case, because the 4 by REP term, 4 by square root REP term also is there. That takes care of this regime, and in between you have this term being important in between. Okay, so that's an expression for CD across all values of Reynolds number. Okay, now let's rearrange all this. Let's try to write this expression. What do we have? We are talking about gravity force minus buoyancy force is equal to drag force. What are we writing? We are writing, well, let's take the next slide. We are writing gravity force minus buoyancy force at which the terminal settling velocity is there. Gravity at which the terminal settling velocity is reached. Gravity force minus buoyancy force is equal to drag force. Substitute for gravity force from here. Substitute for buoyancy force, substitute for gravity force from here. Substitute for buoyancy force from here. Right, you will find that left hand side is pi by 6 dp cube rho s minus rho l, rho of solid coming out of the gravity force minus rho of liquid coming out of the buoyancy force into g, and then the drag force CD, projected area, and half rho Vt square. Can I rearrange this expression? For Vt is equal to square root 4 by 3 dp rho s minus rho l into g divided by CD rho l whole thing square root. Right? Derive this for yourself. Make sure that you get this expression. Don't go forward until you derive it for yourself. Right? It just has to simplify from here to here. Now, if I tell you that I have a particle, let's say 1 millimeter in diameter, dp I know. Let's say it has a density 1500 kg per meter cube. Rho s I know. It is settling in water. Rho l I know. G I know. Rho l I know. Will I be able to calculate Vt? I won't be, because I don't know the value of CD, and CD depends on Reynolds number itself, and from this expression, and Reynolds number itself has a Vt term in it, right? So this is little difficult to calculate. So what we can do is we can look at the extreme regimes. We can look at a regime where Reynolds number is far less than 1, and we can look at a regime where Reynolds number is greater than 1000, let's say turbulent regime if you like, or inertial regime if you like, where CD is 0.44. Let's do that. So this was our expression for Vt from the previous slide. Okay. Now let's look at one extreme, creeping flow regime. Creeping flow regime means Stokes regime. Means CD is 24 by REP. So if you substitute CD is 24 by REP, you substitute that here. CD is equal to 24 by REP, you substitute here. And rearrange, you will find that terminal velocity is 1 by 18 dp square rho s minus rho l into g divided by mu l. Don't go forward until you derive this expression, until you get it by simplifying this expression. Right? So if Stokes regime is valid, if Reynolds number for the particle is far less than 1, then we will find this is the expression for terminal settling velocity. We will use it for calculation as we go along in a while. If you look at the turbulent regime, means Reynolds number greater than 1000. This implies that, well, let's not look at this just now. Don't worry about this just now. Don't worry about this just now. dp Vt by L. So this is greater than 1000. Don't worry about this just now. Okay. Then CD is 0.44. I can put that here and get an expression for Vt. Do that, simplify it for yourself and get it for yourself. Okay. In general, it may not be liquid, it may be any fluid. In that case, we are going to define rho p, particle Reynolds number, as dp rho f, density of the fluid, Vt divided by mu f, viscosity of the fluid. Then in the creeping flow regime, this is the demarcation. In the creeping flow regime, Vt is dp square rho p minus rho f into g divided by 18 mu f. And in the turbulent regime, Reynolds number greater than 1000, it will become 1.75 dp rho p minus rho f into g divided by rho f. Okay, we'll use it for our calculations now. So imagine, let's take several examples. Imagine that particles are small, let's say 100 microns. Okay, 100 micron is 100 into 10 raised to minus 6 or 1 into 10 raised to minus 4 meters. Take care of units. Rho of the particle is 1050. Rho of the fluid is 1000. Mu of the fluid is 0.001. This is like water. So it's like a small particle settling in water, like a dust particle settling in water, or a large droplet. These days we are worried about how droplets ejected by people when they sneeze and cough, how they settle in air, right? So this first case is like a dust particle settling in water. Next is a small droplet settling in air. Let's say droplet is 10 microns. 10 microns is 10 into 10 raised to minus 6 meters, that is 1 into 10 raised to minus 5 meters, 0.00001. It is settling in air, so that droplet is of water. Rho p is 1000. Rho f, air, typically air is 1, density is 1, 1.2, 1.6, 1.16 and so on, don't worry about it. Viscosity of the air is about 10 raised to minus 5. Okay. You could have large droplets settling in air like raindrops. You have a raindrop 1 millimeter in size. Rho p is 1000, rho f 1, mu f 10 raised to minus 5. Or you could have particle which is lesser dense than the fluid. So you have a gas bubble in water. So bubble diameter is, let's say, 1 millimeter. Density of the bubble, now particle in this particular case, is 1. Density of the fluid is 1000 and viscosity is 0.001. So in this case now, gravitational force will be less. So 1 second, let me just write here. For this particular case, gravitational force is downwards, buoyancy force is upwards, and the buoyancy force is more than the gravitational force because the density of the particle bubble is less than the density of fluid. In this case, the bubble is going to rise upward like the helium bubble that we did in the fluid statics problem. Now, if this is a bubble that is rising, our air or our water flow around is going to be like this. So the drag force is going to be downwards. Drag force is going to be here. So our terminal settling velocity expression would be now the gravity minus buoyancy force. That will be, buoyancy will be higher, it will be negative. Or you can say that buoyancy force is equal to gravity force minus the drag force. So buoyancy force minus the gravitational force would be equal to, in this case gravity force and drag force are in the same direction, plus. Okay. So drag force will be buoyancy force minus gravity force, which means the bubble will rise upwards. Okay. You could have a large particle in water, let's say 1 millimeter particle in water, like an ion exchange resin, right? You have a 1 millimeter ion exchange resin that is settling in water. Okay. I would like you to calculate terminal settling velocity for all of these. Okay. Pause the video, calculate for yourself, use these formulae. Okay, here are the answers. Let's do not for all cases, let's do for a couple of cases. Let's do for one case. Gas bubble in water. Okay. If I have to calculate the terminal settling upward velocity, now it's not settling, terminal rise velocity of the bubble, I need to know whether I need to use this expression or whether I need to use this expression. What does it depend on? It depends on the Reynolds number. But I don't know Reynolds number because I don't know the rise velocity itself. So like the problem that we did when we had Bernoulli equation, we had liquid draining due to gravity from a tank. We had assumed the Reynolds number, did the calculation and checked the value of Reynolds number again. Same calculation we can do. Assume first of all that Stokes regime is valid. So CD is 24 by RE. This is our assumption. We are assuming. If that is the case, then we can calculate the terminal velocity from here, this expression. Now if you calculate this, you can calculate Reynolds number from here. And if you can, now rho f and mu f is fluid It is not bubble now. The bubble is rising. The drag that is caused is flow of liquid around. So it is now rho and mu of the liquid that is causing the drag force. And you can calculate Reynolds number and check whether it is less than 1. Right? So calculate REP using this VT. Check if the calculated Reynolds number is less than 1. Then our assumption is correct. But if not, then what can we do? We can assume that turbulent flow regime is valid. Then CD is 0.44. We can calculate terminal velocity from this expression. Again, we can calculate Reynolds number and check whether our Reynolds number is greater than 1000. Then our assumption is valid. Okay. So calculate. What about this one, last one? You might struggle for this. You might find that this is not valid, nor is this valid. Neither creeping flow regime is valid, nor Reynolds number greater than 1000 regime is valid. Then what you do is you take this CD expression, and put that here. So let me just write that. Our CD was 24 by REP plus 4 divided by square root REP plus 0.4, and REP depends on terminal velocity. If I put this expression here, I will have to solve one nonlinear equation for terminal settling velocity. So solve that. You might have to do that for this last case. Okay, do that for yourself. Do all these cases for yourself. Okay, pause the video. Do it. The problem. Do for yourself. Check with your friends. Pause the video. Okay, here are the answers. Right. Make sure that you get these answers. Now, won't it be nice if I could just calculate, if I just know dP, rho p, rho f and mu f? Won't it be nice that just by knowing these, if I could say whether this is valid, whether the creeping flow regime is valid, or whether the turbulent flow regime is valid? I would like to tell just by knowing these 4 values which regime is valid. Then I don't have to do trial and error. I don't have to assume, check, if not, make another assumption and check, and so on and so forth. Here is what we can do. Okay. Our 2 regimes are here. One is regime Reynolds number far less than 1. These are the 2 regimes. This is REP less than 1. Terminal velocity is given by this expression. This is REP greater than 1000. Okay. This VT, can I substitute that here and make a Reynolds number out of it? I will get this expression. Once you get this expression, Reynolds number is a dimensionless number. So this number also is a dimensionless number. Okay. We are going to call this dimensionless number, this part of the dimensionless number, we are not going to take 18 into account. This part of the dimensionless number. So particle Reynolds number is same as this number divided by 18. We are going to call this as Archimedes number in honor of Archimedes. People have done it later on in his honor. So if Reynolds number is less than 1, what it means is Archimedes number has to be less than 18. And look at Archimedes number. Everything is known. dP is known. Rho p is known. Rho f is known. Rho f is known. G is known. Mu f is known. Everything is known. So just by calculating Archimedes number, if Archimedes number is less than 18, it automatically means that Reynolds number is less than 1, and it automatically means that the terminal settling velocity can be calculated from this expression. Look at the other extreme. Terminal velocity is given by this expression. I can put that here in the Reynolds number definition, particle Reynolds number definition, and rearrange. What we will find is this expression. You will find that left hand side is Reynolds number, particle Reynolds number, 1.75 square root Archimedes number. It's the same expression that is appearing. So if Reynolds number is greater than 1000, means 1.75 square root Archimedes number is greater than 1000, which means Archimedes number has to be greater than 3.3 into 10 raised to 5. So just by knowing particle diameter, density of the particle, rho f, g, mu f, I can calculate Archimedes number, and if Archimedes number is greater than this number, it automatically means that Reynolds number is greater than 1000. It automatically means CD is 0.44. It automatically means this expression is valid. Okay, so exercise for you is to calculate Archimedes number for all these cases. Okay, and check which case Archimedes number is less than 18. Straight away use this expression. In which case Archimedes number is greater than 3.3 into 10 raised to 5. Straight away use this expression. Okay. If Archimedes number is less than 18, straight away use this expression. If Archimedes number is greater than 3 into 10 raised to 5, straight away use this expression. Isn't that better than doing this trial and error, assuming and checking and assuming something else again? Right? That's the advantage of defining Archimedes number. Okay, do this for yourself. Where are these kinds of things important? These kinds of things are important when you are trying to separate solids and liquid. Let's say cyclone separator, right? You will do in your semester 6 in environmental engineering course, trying to separate solid particles from gases, right? So if something is written here, don't worry too much about it just now. It depends on how much time it spends in going around. That's dependent on the velocity, it's dependent on the width, and in that time the centrifugal force has to be enough to take the particle to the wall, and that's how these cyclones are designed. Don't worry about the design of cyclone part. This is where it is important. That's the only thing I wanted to show you. Another example, these are called as rotameters. They help us to measure the flow rate. So if you look at this, what this consists of is a conical or a tube with increasing cross-sectional area. There is something called as a float here, and this float is actually called as float because it is floating in the fluid. If it is a liquid, it is floating in the liquid that is going around. So this is in a pipe, so liquid is going up this pipe. Liquid is going up this pipe, and this float is floating. Again, you can say gravitational force is a downward force, upward force, buoyancy force, and a drag force. If it is floating, then again you can say that gravitational force minus the buoyancy force must be equal to the drag force, and this float is typically denser than the fluid, so therefore gravitational force is more than buoyancy force. The downward gravitational minus buoyancy force is exactly balanced by the drag force coming out of here, and that's a position at which this object, this float, is floating, and there is a marking here. So there are markings on this tube, and you can read the marking, and then this marking you can calibrate, and you can know the flow rate from here, right? So the point where the float is floating, you can know you can calculate the flow rate from that. Now if I increase the velocity, what will happen? Gravitational force is unchanged, buoyancy force is unchanged, but drag force will increase. If drag force increases, there is a net upward force, then this float will go up. But if it goes up, what happens to the cross-sectional area now? The gap between the float and the particle, the gap between the float and the walls of that particle has increased. This gap is here, somewhere here. If the float is there, if the float is somewhere here, the gap is much less. Somewhere here gap is much more. So as the fluid velocity goes up or fluid flow rate goes up, this float will go up, but then because of the increased cross sectional area, the relative velocity of the fluid with respect to float will reduce, and again this float will come to a situation or a new equilibrium, new floating position, where again the gravitational force minus buoyancy force is exactly equal to the drag force. So when the flow rate changes, the position of the float changes, and the calibration that is there on this tube, where the position of the float is, you can calibrate in terms of the flow rate of the liquid through here, and the flow rate of the liquid is the same as the flow rate through this pipeline. So you can know the flow rate of the liquid in the pipeline by knowing the position of the float. So this is called as a rotameter, and it allows us to measure the flow rate. This flow meter is called as a differential area flow meter because area is changing, or a variable area flow meter. Area is varying, and this variation of area is what is allowing us to measure the flow rate. In the laboratory, you will see many places where rotameters are used for measurement of flow. Okay? So this completes our second part of the lecture on flow past immersed bodies. In the next part, what we are going to look at is flow past a bed of particles.